First, we are going to look at a few definitions. The first definition is a relation, which is a set of ordered pairs that are identified by using a bracket. So our relation would have the ordered pairs 2, 6, 1, 3, and -2, 8. In a relation, we have domain and ranges. The domain is the x values, so that would be your 2, your 1, and the -2. The range is the y values, which is 6, 3, and 8. When we write the domain and range, you must write them in order from least to greatest, and we should not repeat any numbers. Now we are going to label a coordinate plane. When we label a coordinate plane, we use ordered pairs. Our first coordinate or ordered pair is 2, 1. So we go over 2 from the origin, up 1, and put a dot. And we'll label that with A. Our next ordered pair is -3, 5. So we go to the left of the origin to -3 and up 5, put a dot, and label that B. Our next ordered pair is 0, -2. So we start at the origin again and then go down -2. We don't need to go over anywhere from the origin and label that C. Our next ordered pair is 4, 6. From the origin, we go to the right 4 and up 6, and we'll label that with a D. For our ordered pair at E, we have -2, -4. So we'll go to the left of the origin to -2 and down to -4 and label that with E. Our next ordered pair is -4, 0. So from the origin, we'll go over to the left to -4, and we don't go up or down because it's just 0. Our next ordered pair is 6, 2. So from the origin, we will go over 6 to the right and up 2. You always go over before you go up or down. And for our last ordered pair, we will have 4, -5. So from the origin, we'll go over to the right 4 and down -5 and label that J. For our coordinate plane, we have our first coordinate quadrant, our second quadrant, third quadrant, and our fourth quadrant. For the first example, we are going to look at a relation and label the domain and range. The domain is your x values. So our domain for this relation is -1, 0, 2, and 3. The range is our y values. So the range for this relation are 4, 5, and 6. When we write the domain and range, we need to remember to write them in order from least to greatest and not repeating any numbers. For example 2, we need to find the domain and range on a coordinate plane. First, we need to label our ordered pairs. Our first one is -3, 1, -1, 5, 5, 2, 4, 0, 2, -2, and -1, 0. Our domain is our x values. We need to remember to put them in order from least to greatest and not repeating. Our domain would be -3, -1, 2, 4, and 5. Our range is our y values, so we need to remember to put those in order from least to greatest and not repeating. -2, 0, 1, 2, and 5. Now we are going to find the domain and range of this shape on a coordinate plane. First, we will find the ordered pairs. We have 0, 4, 2, 1, 0, 0, and -3, 1. So the domain for this shape, in order without repeating, would be -3, 0, and 2. The range, which are the y values, in order and not repeating, would be 0, 1, and 4. Remember, any shape that is closed off, which means it's contained, will have a domain and range between two numbers. Now we are going to look at the domain and range of this figure on the graph, which is called a parabola. First, we need to write the relation of the ordered pairs that are on this graph, which would be -3, 4, 0, 0, and 2, 2. The domain are the x values, so we need to remember to write them in order and not repeating. We have -3, 0, and 2. The range are the y values, which again we need to write in order from least to greatest and not repeating. Our range would be 0, 2, and 4.
Now that we've discussed what domain and range means, we need to discuss exactly what a function is. For something to be considered a function, no x values can repeat. Okay? If you're looking at a graph, the easiest way to determine if any x values repeat is to use the vertical line test. The vertical line is just simply drawing vertical lines on the graph. If the line passes through more than one point at a time, then the relation is not a function. So let's go ahead and draw some lines on the graph. Vertical lines are up and down. And if you notice, when we're drawing vertical lines through all the points on this graph, they're only touching one point at a time. Because it's only touching one point at a time, the dots on this graph are considered a function. All right, so now we've got two more examples that we need to determine whether or not the graphs are functions. If we do our vertical line test, right now it's passed the vertical line test so far. But when we get to the y-axis, you'll notice that the vertical line goes through 2 points at a time. Therefore, we don't even need to move on any further than we already have. We know that this is not a function. So let's look at our second example. Go through your vertical line test, passes. It's continuing to pass until we get to our positive 2. So this is not a function. Well, the reason that those two examples were not functions was because in our first example, our x repeated at 0. In our second example, it was not a function because x repeated at 2. And I just wrote it like that simply because I don't have enough room on the slide. On your examples, you'll want to make that a little more clear. Another way to organize coordinates is to use a mapping diagram. A mapping diagram could either be represented by two ovals or large sets of parentheses. In your first oval, you're going to put all of your domain value, your x's. In the second oval, you'll put all of your y values. You need to arrange your values from least to greatest. Okay, so let's work on our x values first. Our smallest x value is -1. So we've got to put -1 in there. Now we've used it and we can remove it. The next would be 0, then 2, and 3. So those are all of our x values, and we've arranged those. Now remember, you do not want to have any values repeat. So no values are going to be written more than once. All right, so now let's move on to our y values. Our smallest y value is 4. Now, if you notice, 4 is written twice. Okay, it appears twice in our ordered pairs, but we only write it once when we do our mapping. Our next smallest y value is 5, and then 6. In mapping diagrams, you don't have to have the same number of x and y values because, again, we can't have any numbers repeat. From here, we actually have to organize what numbers belong with each other. Well, our first ordered pair was 2, 4. So we need to draw a line from 2 to 4. That's letting us know that those two numbers belong together. Our second ordered pair was 3, 5. Again, draw my line. -1, 4, and then 0, 6. So this is kind of just like we did when we were back in elementary school when you had to do matching. Same thing, we're matching the numbers up from the ordered pair. So we just connected the ordered pairs with a line. And then now we need to answer the following question. Is the mapping a function? Well, if you remember what a function is, it means that x doesn't repeat. Okay? So if x does not repeat, one only has one line coming off of it, so one's not written more than one time. 0 only has one line coming off of it. 2, one line, and 3 only has one line. So this is a function. Okay, so now we've got two more examples of mapping diagrams. Again, we have to organize our mapping diagrams in order from least to greatest, and we can't write any of our values more than one time. In our first example, the order should be -1, 0, 3, and 4. For our y values, they should be arranged -2, 2, and 5. You can cross them out if you'd like, if that helps you. And now we need to connect the matching ordered pairs. So we've got to do our matching here. Our first ordered pair is 3, 2. So we need to connect 3 and 2. The second ordered pair is -1, 5. So connect those two numbers. 4, -2. And then 0, 5. So, is this map a function? Well, yes it is, because no x values repeat. In our second example, we need to arrange our x values. So we've got 1, we've got 3 that shows up twice, but we're only going to write it once. And then 6, so 1, 3, 6. For our y values, we should have -3, 1, 3, and 4. Now we've got to do our matching. So 3, 3, draw our line. 6, -3, 3, 4, and then 1, 1. All right, so is this map a function? If you notice, in our x values, our number 3 has 2 lines coming off of it, meaning that it's been used twice. Therefore, our x value is repeating. If our x value repeats, it is not a function. Another way to organize ordered pairs is using a table. From the table, we can take out our values and organize them in set notation. So again, domain is talking about our x values. If we're talking about our x values and we need to get this in set notation, we would say that D for domain equals, and then we've got to put our curly brackets. Have to do the brackets. Again, in set notation, you order from least to greatest, and you cannot write numbers more than one time. So our smallest domain value would be 0, then 1, 6, and 9, and we're going to close off our bracket because that is all of our domain values. Notice that we did not write 1 more than one time. Even though it repeated itself in set notation, we can only write it once. So therefore, our range in set notation from least to greatest is going to be -3, -2, -1, and 3. Again, notice that we did not write -2 more than one time. We only write it once. So now we need to decide, is this relation a function? Function tells us that x cannot repeat. Our x values repeated at our 1, so this is not a function. Another example with the table for domain and range. Again, set notation. And we have to order from least to greatest. Our smallest x value is 14, then 18, 20, and 21. Use your brackets. For the range, we have 4.25, then we have 4.40, I'm just going to put 4.4, then our next value should be 5, or 5.0, and then 5.25. So, is this relation a function? Again, function means that x values cannot repeat. Well, we didn't have any x values that repeated, so this is a function. This is a function.
A function rule is an equation that describes a function. Looking at this table, we're going to think, what are we doing to the x value to get the y value? For this first example, one thing we could be doing is multiplying by 5. 1 times 5 is 5. We could also be adding 4. 1 plus 4 is also 5. Let's look at the second example. 2 times 5 is not 6. However, 2 plus 4 would give us 6. We can also do 3 plus 4 to give us 7. And 4 plus 4 would give us 8. So we can assume that when we add 4 to these x values, we get these y values. The function rule for this table would then be x plus 4
equal y, or f of x. F of x is just notation for function rule writing. So f of x also equals y. So again, you can write f of x equals x plus 4, or you could write y equals x plus 4. And that would be the function rule for this table. Real-world function rules. The exhibit of a desktop computer is about 20 times the size of a normal-sized desktop computer. Write a function rule to describe this relationship. We're going to let n equal the normal-sized computer, and we'll let L of n equal the length of the larger-sized museum's computer. So the function rule would look like this. L of n, which is also f of x, just another function notation, another way of writing this function rule. L of n equals, and we look back in the story, it says it is 20 times the size of the normal size desktop. So to show 20 times the size of a normal desktop would be 20 n. At a supermarket salad bar, the price of a salad depends on its weight. If salad costs 19 cents per ounce, we're going to write a function rule. The function rule for a salad would be f of x equals, we're going to write 19 cents, 0.19, and per is going to mean times, so we're going to write 19x. So we're going to times it by the ounces of salad. With this function rule, 0.19x, we could compute how much an 8-ounce salad would cost. The 8-ounce salad would cost, we would do 0.19. Instead of x this time, we're going to put in parentheses 8 for the 8 ounces. Close my parentheses. That would give us total price of $1.52, which is 0.19 times 8. And to review, if the salad costs 19 cents per ounce, then the function rule f of x would equal 0.19 times x, or the ounces. To use the function rule for an 8-ounce salad, we would use 0.19, and instead of our x value, we would put in 8. Times it by 0.19 gives us $1.52 for the salad. Alright, so we've already talked about writing function rules from a table. Now we're going to talk about how you write a function rule as an equation and what the different parts of the equation are represented by. When we were talking about the tables, your x and y coordinates were given to you in the table. Therefore, when you're looking at the actual equation or the function rule, the x and the y values are the ordered pairs. They're the coordinates. If you're given an equation but no coordinates, you can create a graph by using a t-chart. And we're going to talk about those on the next couple of slides. Alright, so if you look on the right side of the slide, you will see our t-chart. In the first column, you have your x values. The middle column, you write the equation. And in the last column, you get your y value. Our steps to graphing the equations is if your equation's not already solved for y, you need to do that first. Then we make our chart, and we're going to choose up to 4 x values, and you need to have a negative x, 0, and a positive x. And then from there we're going to graph the coordinates that we have in the table. So let's practice. On the right side of the slide you'll see our t-chart. In the t-chart you want to have your x value. In the middle column you write your equation, and in the last column you're going to find your y value after you've plugged x in to the equation. So our steps for graphing these equations are going to be solve the equation for y if it's not already solved for y. Then we draw our t-chart if it's not already drawn for you. And then you need to pick up to 4 x values using a negative x, 0, and a positive x. So you can choose any numbers that you want. Generally it's nice to keep the numbers under 5 or 6 so your graph isn't going to be extremely large. And then once we have our coordinates, we graph them. So let's make up some x values. I can pick any numbers I want, but I'm going to say -2, -1, 0, and 2. From here, I'm plugging my x values into the equation. So I'll say 2 times -2 plus 3. Well, 2 times -2 plus 3 gives me -1. So my y value is -1. 2 times -1 plus 3 gives me a +1. 2 times 0 plus 3 gives me a +3. And then 2 times 2 plus 3 gives me 7. Therefore, my ordered pairs in the first row are -2, -1. Second row, -1, +1, 0, 3, and 2, 7. And those are what we would graph on our coordinate plane. Alright, so now that we've practiced just filling in the t-chart, let's actually do an example where we create the t-chart and then graph our coordinates. So again, you can pick any x values that you want to plug into the equation. However, in our situation, because we have a fraction, 3/4, it's best if we choose an x value that is divisible by 4, so we get an even number as our answer. So I'm going to use -4, 0, and +4. And I'm only going to choose 3 or else our graph would not fit on the screen. So we're going to say 3/4 times -4 minus 1, which gives us -4. And then 3/4 times 0 minus 1 gives us -1. And 3/4 times 4 minus 1 gives us 2. So our coordinate that we're going to graph first is -4, -4. So you come to -4 on your x-axis and -4 on the y-axis, and you plot your point. Then we go to 0, -1, 0 on the x-axis, down 1. And then 4, 2. So 4, +4 on the x, and up 2. So we've got our 3 points, and from here we just connect our dots to make the graph. Your line should be nice and straight, and that's all you've got to do for graphing from a table. Let's do another example. Alright, so this is going to be our last example of using the t-chart and graphing. Again, you can choose any x values that you want. I'm going to use -2, -1, 0, and +2. We're plugging our x values into the equation. So -2 times -2 plus 2, which gives us 6. -2 times -1 plus 2, which gives us +4. -2 times 0 plus 2 gives us +2. -2 times 2 plus 2 gives us a -2. Alright, so we've got to plot our coordinates. We have on our x -2 and then up 6. So plot our point. Then you have -1, 4. Plot our point. 0, 2. And 2, -2. So if we connect our dots, oops, and again your line should be straight. I apologize for my line. But your line should be a negative line and should go through all of those points. Okay, so now we're going to talk about arithmetic sequences. The formula you see on your slide, A of n equals A plus the quantity n minus 1 times d. Now, if you look on the slide, you have your first term in the sequence is your A values. So follow your arrows, look at both A values. The term that you're looking for is your n value, and d is your common difference. So now that you have this formula, let's put it to use. Okay, so in arithmetic sequences, we are going to find a specific term and the sequence. And in our example, we need to find the 2nd, 5th, and 9th terms. As discussed on the slide before, your n is the term that you're looking for. So when we plug this in, if we're finding the second term, we would say a of 2 equals 2 plus 2 minus 1 times 3. If you say 2 plus the quantity 2 minus 1 times 3, you get that a of 2 gives you 5. If we're looking for our fifth term, you would have a of 5 equals 2 plus the quantity 5 minus 1 times 3. Plug that in your calculator and you get that a of 5 equals 14. And then if we're looking for our ninth term, we would have a of 9 equals 2 plus the quantity 9 minus 1 times 3. And a of 9, when you plug that in your calculator, is going to be 26. So here's another example of arithmetic sequence. However, in our example, they've given you instructions in a little different format that they did in the previous example. They want you to find the next 2 numbers in the sequence. Okay? In order to do this, we have to figure out which numbers do I already have in the sequence. Well, I have the first, second, third, fourth, and I need to find my fifth and my sixth terms. Those would be the next 2 numbers in the sequence. So I'm looking for the fifth and the sixth. Those are going to be my n values. Something else that we do not know in this problem, or that was not given to us that we have to figure out, is our d, our common difference. In order to find the common difference, you need to look at the pattern of the numbers that you're given. Well, how do I get from -5 to -2? I add 3. How do I get from -2 to +1? And adding 3. From 1 to 4, I add 3. So my common difference is a +3. So let's go ahead and plug these in. If I'm looking for my fifth term, I would say a of 5 equals, and a is my first term in the sequence. Well, my first term in the sequence that they gave me is -5. So -5 goes in for a, plus the quantity, and I'm looking for the fifth sequence, so again I'm plugging in 5 minus 1 times, and I'm multiplying by 3, because as we said up top, our common difference was 3. When you plug that into your calculator, you get that a of 5 equals 7. Then we've got to find also our sixth term. So our fifth term was 7, and our sixth term we have a of 6 equals -5 stays the same. -5 is always our first number in the sequence, but our n changes because we're looking for the next number in the sequence, so that should be 6 minus 1. And our common difference stays the same as well. Okay, so plug that in your calculator and you get that a of 6 equals 10. So let's plug that in and let's see if this all still makes sense. Does 4 plus 3 equal 7? Yes, it does. Does 7 plus 3 equal 10? Yes, it does. Therefore, those are the next two correct numbers in our sequence. All right, we're going to do one more example on arithmetic sequence. Again, in this example, it's asking us to find the next two numbers in the sequence. So we need to find two more numbers. Well, I've already got the first four numbers, so I'm still looking for the fifth and sixth numbers in the sequence. I don't know my common difference. It's not given to me. I have to figure that out. So how am I getting from -6 to -10? We are subtracting 4. -10 minus 4 give us -14. -14 minus 4 gives us -18. Excuse me, that should be a 4. Make that correction. Okay, so we're subtracting 4 every time. That's our common difference. Therefore, if we're plugging this in, and I'm looking for my fifth term, I'm plugging 5 in for n, because n is the number I'm looking for in the sequence. My first number in my sequence, which is my A, is -6, because that's the first number that they gave us in our sequence, plus the quantity, 5 minus 1, and our common difference this time is a -4. Okay, because we were subtracting 4 for all of our differences, so our common difference is negative. All right, so when we plug that in, we get A of 5 equals -22. And if we're looking for our sixth term, which is our second number that they're asking for in the sequence, I still start with my same A, which is -6, plus the quantity 6 minus 1 times -4. When I plug that into the calculator, I get the A of 6 equals -26. So let's check it out when we plug them into the sequence. We have -22, and then we have -26. To get from -18 to -22, I subtract 4. To get from -22 to -26, I subtract 4. Therefore, these are the two correct numbers in our sequence.
Direct variation, what it is and how do you know when you see it? If you notice on the graph, as x is increasing, y is also increasing. As x is decreasing, y is also decreasing. So the thing to remember is that they're going in the same direction. To look at the graph and know whether it is a direct variation is to know that the graph goes through the origin. If the graph goes through the origin, the line, then it is a direct variation. Direct variation, the equation for a direct variation is y equals kx. K is your constant. Constant meaning it will not change. That number will always be the same in the equation. There are a few ways you can write a direct variation equation. One is y equals kx, and then if you solved for k, you would get k equals yx. So if you're looking for k, this is a great equation to use. Also, the shortcut is to use for when we do word problems later on. You will do y over x equals y over x. Okay, here's some examples of direct variation.
first one, you're given a table. It's asking you to find the constant of the variation. Constant meaning k. Okay, and we said we can use this. K equals y over x. So what you need to do, since you already know it's a direct variation, you take one of your y coordinates. In this case, I'm just going to use the first one, and do 12 over, my x to that is 6. And what is 12 over 6? It reduces to 2. So therefore, k is 2. And so your constant of that equation is 2. Here is another example of direct variation. We know that k equals y over x. So we are going to once again use this equation to find the constant. So what is y? Well, I'm just going to use my second point this time. So I'm going to use 5 for y, and if I use 5 for y, I have to use 15 for x. And so 15 or 5 over 15 will reduce to 1 over 3. So my constant is 1 over 3. Here is another example. We know that k equals y over x. So we're once again going to use that to define the constant. This time I'm going to use negative 10 for y. And if I use negative 10 for y, I must use negative 40 for x. It does not matter which point you use. And so when I reduce this, a negative divided by a negative will be a positive, and it will reduce to 1 over 4. Therefore, k equals 1 over 4. Now we are trying to determine if the equations given are a direct variation or not. And if it is a direct variation, then we need to find the constant. Okay, y equals 5x. Well, our direct variation equation says y equals kx. So we have a y, we have a k, and we have an x. Therefore, yes, it is a direct variation, and our k would be 5. In the second example, we do the same thing. Y equals kx. That is our equation. We have a y. We have a k. We have an x. But we have an extra term right here, the plus 1. There is nothing in our regular equation that is plus or minus anything. So therefore, it is not a direct variation. So we have no constant to find. Okay, we were once again trying to find out if these equations are a direct variation, and if it is, what is the constant? Now, we know y equals kx is direct variation. However, if you look at this equation, we do not have y by itself, so we can't compare it to the original like we did in the earlier examples. What we must do first is solve for y. So how do we solve for y? We would divide both sides by 2. So we would get y is equal to 5 over 2, divide each term separately, plus 1/2. Now we can look at and compare it to y equals kx. We have a y, we have a k, we have an x, but we have the extra term. So no, it is not a direct variation. So we do not need to find k. Second example, still y equals kx is what we're looking at, but it is not equal to y. So we need to solve for y first. We will do that by first subtracting the 5x from both sides of the equation, and when I do that, I will get negative 6y equals negative 5x. Still need to get y by itself, so I will divide by negative 6 on both sides. It's a negative. and I will get y equals 5 over 6x. Does that look like y equals kx? Yes, it does. And so my k is 5 over 6. We will now use direct variation in solving some word problems. The key to these is the words varies directly. If you see that in a word problem, then you know you have a direct variation equation to set up. The second thing you want to do when looking at these is you want to identify what you are comparing. The word before varies directly will be your y, and the word after will be your x. We will now do some examples. Here is our first word problem with direct variation. Given that y varies directly with x and y equals 28 when x equals 7, find x when y equals 52. This we're going to use, this is our shortcut of the direct variation that I showed you in the beginning of the lesson. So we're going to do y over x equals y over x. So therefore it's going to be 28 over 7 equals 52, and I do not know what x is, so I'm just going to write x. And then we will solve for x. What you do is you multiply 7 times 52, which is going to give you 364, and then you divide by the number next across from the variable, which in this case is 28. So 364 divided by 28 will make x equal to 13. And now I have answered this word problem. Okay, here are two more examples using direct variation. So given that y varies directly with x and y equals 4 when x equals 3, find x, so x is what we're finding, when y equals 12. So we are going to once again use the shortcut and do y over x equals y over x. So it will be 4 over 3 equals 12 over x, because I do not know what x is. So what I do is multiply the two numbers that are across from each other, which is 3 and 12. So that will give me 36. And I always divide by the number across from the variable. So that is 4. So 36 divided by 4 will give me 9. So x equals 9. My second one, I'm going to do the same thing with the y over x. So I'm going to do 6 over negative 5 equals, I don't know what y is this time, and x is negative 8. I'm going to multiply the two numbers together, which is 6 and negative 8, to give me negative 48, and I divide by the number across from the variable, which is negative 5. A negative divided by a negative is a positive, and so I get 48 over 5. I cannot simplify that anymore, so y is equal to 48 over 5. Or you could divide it out and get a decimal if you want to.
The distance a car travels varies directly with the amount of gas used. A car uses 8 gallons of gasoline to travel 290 miles. How much gasoline will the car use to travel 400 miles? All right, so the first thing we need to do is locate the important information in the problem. Our first important information is varies directly. Whatever we're comparing before varies directly is our y, and whatever we're comparing after varies directly is our x. So I like to go ahead and write that out in words so I don't forget what y and x equals. So if I'm using my shortcut, k equals y over x, I can say that my y is my distance and that x is my amount of gas. Well, it told me that my distance was 290 miles. And it told me that the amount of gas that I used when I drove 290 miles was 8 gallons. So if I use that shortcut that we taught you earlier, you're going to say y over x is equal to y over x. Well, the question that they're asking us is how much gasoline will the car use to travel 400 miles? We don't know how much gasoline, therefore we don't know the amount. So that stays in x. But we do know how far they want us to travel, which is 400 miles. From here, we set up our proportion where we cross multiply. So 8 times 400 is equal to 290x. To solve for x, you divide both sides by 290. So when you say 3,200 divided by 290, you would get that x equals 11.03 gallons. And you need to write gallons because this is a word problem. So you got to write your unit of measure. Julio's wages vary directly as the number of hours that he works increases. If his wages for 5 hours are $29.75, how much will they be for 30 hours? Again, we need to locate varies directly. Whatever we're comparing before varies directly is our y, and whatever is after varies directly is our x. So we have our wages over hours. Well, it told us that our wages were $29.75 when we worked 5 hours. Okay, and we've got to set up our proportion. Well, they want to know how much will his wages be if he works 30 hours. So 30 hours should go on the bottom. And we don't know the number of wages, so we leave our y up top. Again, cross multiply, and we have 30 times 29.75 equals 5y. Apologize for the stray line there. So all we did was cross multiply. Okay? To solve for y, you have to divide both sides by 5. And you get that y equals $178.50. You need to write your dollar sign because it's a word problem. So we've got 4 graphs shown on this slide, and we want you to say whether or not each graph is a direct variation. Direct variation in a graph simply means that it's a straight line through the origin. So you'll need to write that on your notes. Straight line. Straight line through the point 0, 0, which is the origin. Well, our first example, our first graph, does show us a straight line, but it does not go through the origin. Therefore, it is not DV, direct variation, and that's how we abbreviate direct variation, is with a D, period, V. Period. Direct variation. The second line is supposed to be an example of direct variation, but the line is not quite perfect when it shows up on this graph. Okay? So draw a circle big enough to cover up that little gap and do it right over the origin. Okay? And then put yes, because that would be direct variation, because it is a straight line that passes through the origin. Our third graph is a vertical line. It does not pass through the origin, so it's not DV. And then our last example is a curved line that passes through the origin. Well, that's not what the definition says. It has to be straight. So this last graph is not direct variation. The last topic we're going to discuss in Chapter 5 is inverse variation. You see 2 equations written on your screen at this point. Those both are the same formula for inverse variation. However, one of the equations is solved for k, the other equation is solved for y. Just like with direct variation, we gave you 2 different equations that you could use. Same thing for inverse variation, just depends on which one's easier. Inverse variation is a curved line that does not pass through the origin. Okay, so now we've given you a table, and I want to know whether or not this is inverse variation. We need to write the equation. Well, if you remember, one of our formulas is x times y equals k. Again, k is standing for your constant. So in order for it to be an inverse variation, all of your constants must be the same. So if we say 4 times 15, we would get 60. 6 times 10 gives us 60. And 10 times 6 also gives us 60. Therefore, our constants are all the same. So this is inverse variation. And the equation would be x times y equals 60. In our second example with a table, we need to do the same exact thing, x times y. Well, 2 times 1 gives me 2. 5 times 2.5 gives me 12.5. And then 8 times 4 gives me 32. These are not all the same numbers. They are not constant. Therefore, this is not inverse variation. If it's not inverse variation, then there can't be an equation for inverse variation. So we abbreviate with IV for inverse variation.